What's the screen?
Yes, sir.
Here in this photoelectric effect, what is the input? What can you consider as input?
Input.
And what is the output?
Input is light, output is the photoelectrons.
Yeah, you can think like that. So suppose if the light intensity is say something, so that will correspond to n photons, right?
Yes, sir.
If light intensity will correspond to n photons per second, and then per unit area. Is that right?
Yes, sir.
So now, because of this, there will be some current here, right?
Yes, sir.
So can you relate this current to this intensity of the light? How do you relate the current to the intensity of light, that is n photons per second per unit area?
Into area, sir.
No. Current is what? Unit A. A of what?
But the intensity into it.
No, you are not understanding. You're just telling a formula.
Ah,
See, what is current? Current is charged by time, right?
yes, sir.
Okay, so you have to find the total charge which is passing through this wire in unit time. Okay, so if there are n photons, how many electrons will come out?
N electron.
So n electrons will come out, right? So n electron means what is the charge? N into E. Okay, this is the total charge in 1 second.
Yes.
Okay, suppose I assume this area is there, but that also you can read if you want. So the main thing is the current is proportional to N.
Yes, sir.
So current is proportional to the intensity. Okay, does it depend on anything else?
No, sir.
Now, and this current is saturation current. This current is saturation current because the thing is, suppose if there are given n electrons here, suppose the n electrons don't reach this plate, okay, but they are still hanging around here. Then will there be a current here proportional to n? No. Okay, as soon as the electron comes here, it has to reach this plate. No, only then the current will flow.
Yes, sir.
Okay, so if the voltage V is high, here the voltage, this should be positive voltage, right? To attract the electrons. So V is sufficiently high. As soon as the electron is created here, it will reach this plate.
Yes, sir.
So then this relation is valid. Okay, but suppose instead of this positive voltage, I apply negative voltage, what will happen? It will repel the electrons, right?
Yes, sir.
So this negative voltage is very high, then will completely stop. Okay, so that minimum negative voltage which will stop these electrons from reaching this is called the cutoff voltage.
Yes, sir.
Okay, so that's what is happening here. See, as soon as you keep increasing the voltage, okay, so if the voltage is increased beyond a certain extent, as the electron is emitted, it will reach this collector plate and will give the current. But less than that voltage, as the voltage is increased, the current will keep on increasing. Okay, and this saturation value of current depends only on the number of photons that are emitted, or the number of electrons, which is same as the number of photons emitted. So basically the photocurrent, which is the saturation value, is proportional to the intensity of the incident light.
Sir, what is that y-intercept, sir?
What is the
Y-intercept. That graph.
y-intercept? that will correspond to the, it's not of significance. It will correspond to voltage, applied voltage being 0. So without being applied voltage, see, even if there is no positive voltage to attract these electrons, as soon as these electrons are emitted, it will have some velocity, no? Okay, when the applied voltage is 0, here also its voltage is 0. Okay, so electric field is 0. Okay, so even without acceleration, whatever is the velocity, initial velocity here, with that velocity will keep continuing and will hit this plate. Right?
Okay.
So that also will give rise to current. But if the initial velocity is in this direction, it will go and hit this wall. Okay, but chances are that there are some electrons whose velocity is towards right. So all those electrons will go and hit on this plate and give rise to current. So that thing corresponds to current which is flowing without the potential difference. Okay, so to stop the current completely, I have to apply electric field in the reverse direction. So in the case of electron, the electric field should be this way, because the electron will feel the force in the opposite direction. Okay, that is possible if this is negative. Okay, because electric field direction from higher potential to lower potential. If this is negative means 0 is higher potential compared to that, so electric field towards right. In that case, the electron will feel the force towards left, so it will stop the electron from reaching this plate. So the minimum voltage which will stop the electron, that is called the cutoff potential. That is this value. Got it?
Yes, sir.
Okay. We'll move to today's topic. And any questions from last time?
No, sir. Everything is clear.
Okay. So this is a chapter on atoms. So structure of atom. So these are different models of atom. So Dalton, what is his contribution to the understanding the structure of atom? These are all the elements are made of fundamentally the same.
Okay.
And they are called atoms. Like you can say 2% have the same capability because they have the same physical brain. Okay, so that way everyone is same. So similarly, every material is composed of the same elemental at the elementary level minute particles called the atom. Okay, and at that time when he gave this theory, he thought atom was invisible, but that is not true later. Okay, you can divide atoms into electrons, protons, and neutrons, and proton also you can divide. But at that time of his understanding, he assumed the atom is indivisible and atom is stable and electrically neutral. Okay, after that thing, he had Thompson model. Okay, Thompson model, this is the picture. Okay, the four of the positive charge is distributed in the four of the atom, and the negative charges are just spread energy uniformly. Okay, but this is not a true picture, right? Okay, but what is his contribution to understanding the atomic structure? Thomson's contribution.
Electrons, they are spread like that. No, sir.
Yeah, his contribution is discovery of electrons. Okay, he found the electrons are there inside the atom, but the way in which it is distributed in the atom, that is wrong. But electron as a part of an atom, his contribution, that was his contribution. So according, if you have this model, we have atomic spectra also, which was give out radiation in particular frequencies. Okay, and also scattering of alpha particle. Alpha particle is positive charge, negative charge. What is alpha particle?
Helium 2 plus, sir.
Yeah, what is helium unit is made of?
Two proton and two electrons. Sir.
Two protons and two neutrons, nucleus.
Two electrons.
Yeah.
Nucleus, okay, two proton and two neutron.
2 neutrons.
Yes, sir.
So the charge of alpha particle is how much?
In it is He2 plus means 2.
Plus 2e. Okay, it is
Ah.
helium. It's helium ion. It's 2e. So when you try to hit this atom with this alpha particle, so if it will get attracted by this negative charge and repelled by this positive charge, right?
Yes, sir.
So wherever this alpha particle hits, because of this positive charge, it might get deflected, or because of the negative charge will get attracted. Okay, so but the amount of deflection should be constant throughout the volume. Okay,
Yes, sir.
but in reality that's not observed. No, if you hit alpha particle with this atom of a gold foil, most of the things will pass through. Most of these alpha particles will pass through. Okay, only very few will get deflected, and the deflection is also strong. It's almost like turning back U-turn. Okay, so that is possible only if 4 of the positive charge is concentrated in a small place at the center, and the remaining place is empty. Okay, so this alpha scattering experiment done by Rutherford. Okay, so this is the picture. So most of the things are passing through without not much deflection. This one is going straight. Okay, I only as you get closer, it's getting deflected, but some of them are getting strongly deflected. Like this one, it's 180 degrees turned back. Okay, so these sort of things is possible only if the 4 of the positive charge is concentrated in a small place,
Yes, sir.
not as distributed in Thompson model. Okay, so this is the failure of Thompson model. So this is a realistic picture based on the alpha particle experiment. Okay, but there is some limitation to this Rutherford. This experiment is done by Rutherford. Okay, so he gave this model. So, but there are some limitations to this model. What are the limitations? Stability of atom. Okay, and spectrum of the hydrogen atom. Okay, he cannot explain it, that spectrum cannot be explained in this model. Okay, so why is stability of an atom a problem in this Rutherford picture? If Rutherford picture is, why is the atom not stable?
Electron is confined to its particular cell, no, sir.
Yeah,
If it moves out of that cell, means it can lose or gain energy.
so not that.
Goes to higher.
It's moving in a circular path, no? The electron.
And
Okay,
that is what
so
concerned.
so is it accelerated or not? This is a nucleus. Okay, the electron is moving like this. So this is say uniform circular motion. So is there acceleration or not?
No, sir.
Direction of velocity is changing, no? This is always tangential. So the direction
That
of
is
velocity.
radial acceleration, sir, no tangential acceleration.
No, but overall, if you combine both total motion, there is change in direction of the velocity. Okay, so change in direction is also acceleration. So acceleration is there. Okay, so according to classical electromagnetic theory, if the electron is accelerating, any charge particle is accelerating, there will be electromagnetic radiation. So when there is electromagnetic radiation, there will be loss of energy. Okay, and the only energy the electron has got is the kinetic energy. So the kinetic energy of the electron should go down. So if kinetic energy is going down, the velocity is going down. So then the electron has to come to a closer orbit. Okay, so basically it will spiral in, but that's not happening. Okay, so that this model cannot explain. Another thing is hydrogen spectra. It will show some lines like this. If you plot versus frequency, say, and the energy or the intensity, it will have only certain discrete lines. It will emit in, say, particular frequency, and then it will emit in this frequency, and then it will emit in this frequency. But what about the in-between frequencies? Why it's not emitting in these frequencies? Only certain discrete frequency will emit. So that also it cannot be explained by this model. Okay. And this is our spectrum of hydrogen atom groups. So all these dark lines, it means that a particular emission is there. Okay. So right now he's not bothering about how much is the intensity. So just don't bother about what is the exact value of I. If a line is there, he's just putting a line. Okay, not bothering with intensity. So what are the frequencies that are there? It's only some discrete frequencies, not continuous. Okay, and what is Lyman series? You should be knowing, right? This is a spectrum of hydrogen atom. There will be different shells, right? Of electrons. So this is n equal to what?
1.
This is n equal to 2. This is n equal to 3. So when the electron from a higher orbit jumps to the lower orbit, what will happen?
Energy will be lost.
It will emit radiation. When the electron jumps from here to here, it will give out radiation. Okay, because this is a higher energy, E2, this is E1. So E2 is greater than E1. So when electron in second orbit jumps to first orbit, there is loss of energy. So that will go out as something. So that loss of energy is going out as radiation, and this line corresponds to that radiation. Okay, so this one line will correspond to one particular frequency. So on this energy difference, delta E, that will correspond to H nu. Okay, so delta is more means higher frequency or lower wavelength. Okay, so different wavelengths correspond to different levels. So whatever is the delta E corresponding to this, that is different from delta E from here to here. So just by knowing this value, we'll know from where to where it is jumping. So Lyman series is what? All the jumps from any orbit to n equal to 1. If this is the final position, final state, n equal to 1, then we get Lyman series. Okay, n final is 1. What about Balmer?
N equal to 2, sir.
N final. Okay, Balmer series, whatever these sort of transitions from any other state. So this is from n equal to 3 to n equal to 2, and this is from n equal to 4 to n equal to 2. Okay, all these radiation lines that corresponds to Balmer series. And Paschen is what?
N equal to 3.
N final equal to 3.
Okay.
Okay, so right. And with all these wavelengths, we can get a relation between this wavelength and the jump from where to where. So this is Balmer series. Balmer series corresponds to n final equal to 2. That's what I put here. Okay, final energy. So some constant into 1 by final state, that is 1 by 2 square minus any state. This n is greater than or equal to 3. It can be 3, 4, 5 like that. Because to emit radiation, it has to jump from outer orbit to inner orbit. So if to jump from inner orbit to outer, you have to absorb the energy. So Lyman series, n final is 1. Balmer is the first one which was directed. After that, we found out Lyman should also be there. And then Paschen is n final is 3, bracket P fund. Bracket corresponds to the n final state being n equal to 4, and P fund is n final is 5. And the jump will be from higher states. Is this clear?
Yes, sir.
Okay, so one relation you can remember is this one. 1 by lambda is R is what?
R is Rydberg constant. 1 by 9 on R.
Yeah, so some
1.0.
value into 1 by n final square minus 1 by n initial square. So this formula you can remember, 1 by lambda, the energy of the radiation is R into 1 by n final square minus 1 by n initial square. So this formula you should remember. Right. Okay, so the Rutherford model, it cannot explain why the electron is stable. Okay, and also why the spectrum of that radiation, it has some discrete lines, right? So those two it cannot explain the Rutherford model. So that's where the Bohr model came into the place. So here, Bohr model is based on some postulations, some assumptions, but the assumption you have to justify in some sense. Okay, because making assumptions anyone can make, but that assumption should be reasonable and it should explain whatever is. So he assumed when the electron is moving in that circular orbit, it is accelerating, but still there won't be any radiation. Okay, so
Yes,
the orbits are stable and emission of energy without. So this is against the classical understanding of the electromagnetic phenomena. Okay, so without radiating energy, it is moving that circular orbit. Okay, so that makes it stable. And the second postulate is these stable orbits, so it cannot rotate in any arbitrary radius. The radius can have only one specific value. Okay, so so that radius is decided by the condition that the angular momentum corresponding to this particular circular path, that should be n times h by 2 pi. Okay, h is constant, pi is also constant. So this angular momentum proportional to n. And what is angular momentum in a circular path? Angular momentum symbol is L, right? So how is it related to the linear momentum? Linear momentum symbol is P, right?
R times W.
So L is R cross P in the full vector form. And what is the direction of R and P for circular orbit? R is this way, right? Radial.
90 degrees, sir.
And velocity is tangential. So this is 90 degrees.
90.
So R into P into sine 90, right? So sine 90 is 1. So this is R into M into V. So the magnitude of the angular momentum is MVR. Okay, and according to the Bohr's second postulate, this angular momentum cannot be of any arbitrary value. So it is n times h by 2 pi, that is equal to R into mv. Okay, so from this we get the radius. I can put a suffix. Okay, this radius. Okay, so this I can rewrite as 2 pi r. Pi r, and then mv is there. No, mv is momentum. Okay, h by p is what? Wavelength, right?
Lambda.
Yeah.
Okay.
So along this circumference 2 pi r, there will be, and n is 1, 2, 3. It's like natural numbers. Okay. So along the 2 pi is circumference of the circle. Okay. So along this circular path, we should be able to fit in n wavelengths. Okay. So if you have this one wavelength, so if you along this full circle, there will be full wavelengths. Okay, along the full circle. We cannot have 4.5 wavelengths along the circumference. We can either have 4 wavelengths or 5 wavelengths or 6 wavelengths like that. Okay, this is the understanding of this second postulate. And third postulate, it says the electron, if there are two orbits, say n equal to 1 and n equal to 2, the electron can either be here or it can be here. It cannot be in any in-between places. Okay, and when the electron is moving from here to here, this is at a higher energy E2 and this is a lower energy E1. So when it jumps from here to here, there is a foreign energy and that energy will go out as radiation. Okay, that radiation energy is h nu, that is equal to loss of energy, right? So loss means initial minus final. Okay, because when it's giving out radiation, there is loss of energy. Okay, that loss is going out as radiation. So initial minus final. Is this clear?
Yes, sir.
Angular momentum in the circular path is MVR because it's R cross P and P is M into V, and that should be equal to n into h by 2 pi. This is by Bohr's second postulate. From this we get the value of r, p of certain value, and this n will take certain discrete numbers like 1, 2, 3. Okay, so this r is corresponding to this particular value of n. So I put a suffix attached to this r. Even the velocity will have the value corresponding to this particular value of n. So velocity will have a suffix n. So from this we can get the velocity as this one. Okay, and this is the expression for radius of the electron, radius of the electron orbit. So even the radius of the electron orbit cannot have continuous values. Okay, so one important thing you have to remember is the radius of the electron is proportional to what?
N square by Z.
Yeah, just for the hydrogen atom, it is Z is 1. Okay, so it's proportional to n square. Okay, similarly, energy will go as 1 by n square. Okay. So this formula you have to remember.
Yes, sir.
And the unit of energy is electron volts here.
Yes, sir.
So this formula you should remember, and this formula also you should remember. Rydberg constant will be given in the question paper. And radius is proportional to n square. This you can remember. And the exact formula may not be required because. Okay, this is the explanation of this Bohr's second postulate, that n times lambda along the circumference of the circle there will be we can fit in 4 wavelengths. Okay, so either one wavelength can fit in, or 2 wavelengths can fit in, or 3, not 2.5, 3.5 like that. Okay. Okay, solve this question. For an alpha particle of mass m and velocity bombards a heavy nucleus area, its distance of closest approach to nucleus depends on. Understood the question?
No, sir. What do you mean by distance of closest approach?
See, alpha particle is positively charged, no?
Yes, sir.
And the nucleus is also positively charged.
Yes, sir.
So there will be force of repulsion, no?
Yes, sir.
So with that force of repulsion, how close it can come? See, this is nucleus, let the charge be Z into E, and this alpha particle here has got charge 2E, right? Okay, so it will come here and then it will turn back. Like if when you throw a ball from the ground, it goes up and turns back, no? But what did this happen?
But what should put no, sir?
What?
Again, no, sir. Bombard that nucleus. Then you should hit that nucleus, no?
No. If it has got both are positive charge, no? There will be force of repulsion.
So that much of energy they must have given to bombard the earth.
No, what is force between two positive charges? Q1, Q2 by
I
R
think
square. R square, no?
yes, sir.
So if R is tending to 0, what is force tending to?
Infinity.
Okay, but if the alpha particle is like this, it will get deflected like this.
Okay.
But if it's coming head on, it will turn back. That's what is happening at Rutherford experiment, no?
Yes, sir. Yes, sir.
This one, this particular particle, it's going and turning by 180 degrees. right? This is the arrow towards right, and this is the arrow towards left. So just turning back at this particular distance. Okay, if it is little bit away means it will get deflected and go in some direction. Okay, if it is far away means there's absolutely no deflection. But when it's coming head on, as it comes closer and closer, the force will go to infinite, no? So it has to turn back.
Yes, sir.
The same thing is happening here. When you throw your ball from the ground, after reaching a particular height, it turns back, no?
Yes,
Because the acceleration is downwards, initial velocity is upwards. So the initial velocity keep on decreasing, and somewhere it will become zero and turn back. So similarly here also, when it's coming head on, it has to turn back someplace because the force will go to infinite. When it is slightly off, means get deflected and go somewhere. Okay, so this balance of forces will give the how close it can come. So if the okay, we can talk in terms of energy. Initially, suppose there's some kinetic energy, half m v square. So as it keeps going closer, the velocity will go down. Okay, so that will go in increasing what energy?
potential energy.
Potential energy, electrostatic potential energy. And what is the expression for electrostatic potential energy?
It will be Q1 Q2 by Q1
Q1 Q2 by R.
Yes,
Okay,
sir.
here Q1 is ZE into 2E divided by the distance of closest approach. Of course, there is a constant here, A. Okay, it is 1 by 4 pi epsilon naught. So basically, you have to find how it is dependent on the mass. So the distance of closest approach, that is R, is inversely proportional to 1 by A. Other things are constant, right? If the atom is fixed, Z is fixed. Alpha particle is 2E is fixed. Everything is fixed. So the distance of closest approach, which is R. Okay, so this is equal at this turning point, right? Because flow of kinetic energy is converted into electrostatic potential energy. Is that clear?
Yes, sir. At
At
that
the,
point, okay.
at the turning point, here also when you throw a ball from the ground, at the turning point, velocity is zero.
Yes, sir.
Okay, so here the flow of kinetic energy is converted into gravitational potential energy. Okay, similarly here, the initial kinetic energy is half mv square c. At this point, the velocity is zero. So that thing is getting converted fully into the electrostatic potential energy. Okay, so for a given initial velocity, okay, everything is constant in this relation except for r and m. Okay, if you have this m as a variable thing. So the distance of course approach depends on this mass of this incident particle. Instead of alpha particle, you have something else, the mass will be different. So the closest approach is inversely proportional to the mass. Is it clear?
Yes, sir.
So correct option is option C. Okay,
Yes, sir.
this one. Okay.
Inverse
Yeah, I think the same question. How did it come across? Okay, it has come in NEET somewhere. Slightly different form. Okay, I just said it's half mv square. Same question only but different language. Okay, basically we have to do this only. The loss in kinetic energy equal to the gain in the electrostatic potential energy. So everything is constant except for this R and M. If you want to keep that as a variable. Okay, if you fix M, then R is also fixed. But suppose you want to keep this M as a variable, then R is also a variable because other things are constant. Okay, so R is inversely proportional to M. And another thing I can keep it as a variable is the velocity. Okay, suppose I fix M, then the relation between V and R is dependent on, I will go as 1 by V square. Okay, so here the velocity, okay, suppose there is an option of 1 by V square. Okay, so that's also a correct option. Okay, so if velocity is also variable, then the distance of closest approach R goes inversely as 1 by V square. Goes as 1 by V square. Got it now? And this one. This is a trivial question. 2003.
Square by R square.
We just Coulomb's formula. So it should go as E square by R square, and the direction is radial. So this is the one, because R vector is R into R cap, right? So R and R will cancel, and it should be, maybe look at the direction. The electron is moving around the nucleus, so it will be an attractive force. So it will be towards the center, so it's minus.
Option D, sir.
Yeah, so if you assume the nucleus is the origin, and the electron is at the distance r, so it's an attractive force, so it should be D. Okay, the speed of electron in fourth orbit of hydrogen atom is. How do you solve this problem? Fourth orbit, no.
By 4, sir, but I don't know that constant value.
Okay, so basically, centrifugal force should balance this electrostatic force. Okay, so from this I get B as K square by R 1 by N. And this thing should correspond to the fourth orbit. I have to put the radius of the fourth orbit to get the velocity in the fourth orbit. Other than that, how do you get the radius of this fourth orbit?
So V equal to, we have to substitute that NH by 2 pi, sir, or R equal to NH by 2 pi.
Yeah, you have to use the second postulate, no?
Yes, sir.
Okay, V4 into R4. This one velocity is moving as 1 by N. Okay, okay, this one, so from this velocity, so radius of the nth orbit I have to get this velocity is basically we'll get it by using that Coulomb's law only. V square by R V into R. So basically we have two equations and two unknowns. So this is one equation, okay, from equating this centrifugal force to the electrostatic force, and this is the second equation between V and R. Okay, so you have to find both V and R. Two equations and two unknowns. Okay, we can eliminate B. See, from this I can get B in terms of R.
R,
B is 1 by R, no? So here also if I put 1 by R, so okay, here 1 R will go away, so it's 1 by R. So B will become 1 by R square. Okay, combining these two, I'll get the expression for R. So the question so how will you remember these formulas? You have to remember either one of them. Okay, if you can remember this one, or this one. Okay, you figure out what you want to remember.
Okay.
But the basic idea is this one. We have two equations and two unknowns. One equation is by equating the forces, centrifugal force into the electrostatic force, rather than this quantization condition, MR equal to. And he has written this velocity in this form: C by 137 into Z by M, and Z for hydrogen atom is 1. Or you have to remember this formula: velocity in terms of length.
They didn't mention about C values or what. C is speed of the current, sorry, light.
Yeah. Is it that high? Okay. This one, consider third orbit of helium. Using non-relativistic approach, the speed of the electron in this orbit is given as will be okay. K is this one, Z equal to H is Planck constant. Okay. Yes, I think C is the light only. See, here is using the same one, velocity C by 137. C by 137 is 100. No, yeah, C is velocity of light only. Okay, because C by this is approximately 100. So this is approximately 10 raised to 6. No, so that's what he's having here, 10 raised to 6. And this exact thing is 2.2 10 raised to 6. So C by 137 into Z by N. Z is 2 because it's helium. And he's asking orbit in the third orbit. So maybe this you can remember. Velocity is C by 137 into Z by N. This question, alpha particle scattering, Rutherford atom model. I think we have solved this problem. Alpha particle of mass m with velocity bombards a heavy nucleus ZD. Distance of course closest approach. Okay.
1 by M.
Yeah. Basically, at the closest approach point where the velocity is becoming 0, there is conversion of energy from kinetic to electric measurement. So this is the basic relation. From this we get this one. So instead of velocity mass relation, if you want to find how it changes with velocity, it will be 1 by v square.
Okay.
Okay, if mass is fixed. Okay, here the velocity is fixed. So similarly, in terms of momentum, this mv square I can write as p is momentum, right? So p square by m. Okay, so in terms of momentum, it is 1 by p square when mass is fixed. But this is a basic relation. I think this you can remember. Okay, Rutherford scattering experiment: when a projectile of charge Z1, mass M1 approaches target nucleus of charge Z2, mass M2, distance of closest approaches R0. The energy of the projectile is
Energy of the projectile.
say a ball thrown vertically upwards from the ground. It will go straight and come back, right?
Okay.
So this is also a projectile motion, but it's a special projectile motion in the sense where the angle of projection is 90 degrees.
Okay.
Okay, so here also it's projectile in the sense is going head on towards the nucleus and turning back. So in that sense, it's a projectile. Okay.
Okay.
Projectile means it's projected with the velocity. I can also consider this vertically up motion, which is the 1D projectile as a projectile motion. Okay, so the distance of closest approach is R0. So the energy of the projectile is. So energy of the projectile is the initial energy we can consider as half m v square. Okay, so that depends on what? How it depends on other things.
Inversely proportional to that R0 and
But that's not an option, right? If you look at the option, you are not given that is an option. So you have to see whether it's dependent on other things. M1 and M2
charge.
directly proportional to Z1, Z2. So if you write this equation of energy conservation, the distance of closest approach, the half mv square will get converted into 1 by 4 percent into Z1, Z2. It's actually E square. Okay, Z1 is considered as charge. Okay. Charge is actually Z1 into E, but he has considered the charge as Z1. So it is Z1 into Z2 by R0. So if R0 is fixed, okay, then it is proportional to Z1 and Z2. Half in square is the energy. So B is correct. Directly proportional to M1, no. Energy of the projectile. Okay. The final electrostatic energy is proportional to M1, but this is not energy of the projectile, it's energy of the combination. This energy of the combination of the projected mass and the central nucleus. Okay, so this is energy of interaction, it's not energy of the projectile. Only half mv square can be considered as energy of the projectile. Okay.
Okay.
So only option is B. So it's independent of M2. The M2 does not come in this picture. M2 does not come in this picture. Only Z1 and as far as the second one, only the charge comes into the picture. So it depends on charge of second, but it's not depend on the mass of the second. This one. You know what's the impact parameter?
No, sir.
You can also guess it. Okay, it's here. The correct option should be what will be the correct scattering angle. So it will go and come back. So it's 180 degrees. So it should be option B. Option D is the correct option. Okay. So see, this is the impact parameter. So this one which goes straight head on will turn back, right?
Yes, sir.
If it is slightly off, it will get deflected. Okay. So for this particular thing, it is by this much distance, right, from the line corresponding to this head-on collision. So this distance is called impact parameter. Okay. So if B is 0 means it's head-on collision. Got it?
Yes, sir.
So this is impact parameter. Impact parameter is how far it is from the line joining the initial velocity towards the nucleus. So based on that, so impact parameter is 0 means it's head-on collision. In that case, it will fully turn back. So it is 180 degrees. Okay.
Okay.
So it's 180 degrees only for this particular value of B. Other things will get deflected. Okay. Bohr model hydrogen spectra. Total energy of an electron in its stable orbit can be obtained by, this is a theoretical question.
Minus 13.6.
Which option?
Option C, sir.
Option C is 1.36.
Sir, 13.6. Option B.
So it's option B. Oh, they asked in NEET 2020. Okay, this is also 2020. For which of the following Bohr model is not valid? Okay, so you can think of limitation of the Bohr model. Singly ionized helium atom.
Electron.
It's
Singly
applicable.
ionized. Only for one electron species.
Yeah, why is it applicable only for one electron?
I don't know, sir.
See, you are assuming that this is a nucleus. Here there is no restriction, right? It can be anything, ZE. Okay. If there is single electron here, then the force on the electron is this attractive force. And balancing is what force?
Sorry, what, sir?
Electron is there. There is an attraction, no, towards this.
Yes, sir.
And what is the force that's balancing it?
That is a centrifugal force.
It's a pseudo force. Okay, but we can assume it's a force. Okay, so these two are in balance. Okay, but suppose there is one more electron here, or electron here in some other place. So then what is the force on this single electron? This first electron?
Three forces, two electrostatic forces and one centrifugal force.
So that will make it very complicated, no?
Yes, sir.
Okay, so then this orbit will also become somewhat different shape.
Yes, sir.
Okay, need not be circular. So this will make it complicated. So all the calculations we did for Rn, energy in this in a electron orbit. Okay, all these things are made with the assumption that there's only one electron and a single nucleus. This nucleus can have Z anything. Okay, Z can be anything. But as far as the outer electron is concerned, should be only one single electron. If there is some other charge, then there will be force of attraction or repulsion between them. That will complicate the picture, and it's not solvable. Okay, so
Deuteron is only nucleon of the deuterium atom. No, sir. There won't be any electron in deuteron.
deuteron means there will be two protons in the middle.
And
Single
two protons plus neutrons. No,
single.
one proton and two neutrons, sir.
Yeah. Fine. But still, electron is single.
There won't be electron. No, sir. Deuteron means a nucleus of the deuterium atom. No.
No, atom.
Inside
No. Atom. It's this thing plus the outer electron. Since it is single electron, it's still valid. Bohr atom is Bohr model is valid.
So, but the term deuteron means nucleus of the deuterium atom only, no, sir.
No. Hydrogen means whole hydrogen atom, no. So deuteron means
no. I'm asking deuteron. Deuteron means nucleus of the deuterium atom.
no.
You can Google, sir.
No, you can Google it. Deuteron means this one. Atom as a whole. Hydrogen means by hydrogen we understand hydrogen atom, no. Similarly for deuteron means deuterium atom. Okay, but the difference between the hydrogen and deuteron comes because the difference in the nucleus. That way we can say only the nucleus is important. But when you say deuteron, it means the whole atom. So it's actually you don't have to write this term also. It's not a good. Deuteron means deuterium atom. Hydrogen atom, so you don't have to write atom. Hydrogen means hydrogen atom in general. Okay. If you want to say the nucleus of deuteron, then you have to specify either deuteron nucleus or something like that. Here also it says singly ionized helium atom. That means you have to remove one electron from the atom. If you just helium, it means helium atom.
Okay.
So singly ionized neon atom means not valid. Okay, deuteron atom also it's valid because it's a single electron. But neon there are multiple electrons because even after removing this one electron, there will be more than one electron. Okay, singly ionized helium is also single electron. The Bohr model is valid for that. So doubly ionized, what is next to helium? Lithium, right?
Yes, sir.
Lithium has got 3 electrons. Hydrogen, helium, lithium, right? So doubly ionized lithium, that's also valid. Bohr model we can apply for doubly ionized helium, lithium also, because I've got single electron. Because 2 electrons are removed. After removing 2 electrons, it has only one single electron. So for this also Bohr model is valid. Okay.
Okay.
So carbon atom, if you remove 5 electrons, we can apply Bohr model. Okay.
Okay, sir. Fine.
Okay. So this modern physics, the questions will be simple only, except for remembering certain formulas. So that's why the
Calculation will be tough, sir.
no. See, what are the tough calculations here? It won't be tough.
So they are asking in different calculation also, so it will be tougher.
For example, maybe that 1 by n square. So whatever it is, some problem might have little bit lengthy calculation, but everything will be doable. Otherwise, they cannot give it in the exam because everyone has to do it, right?
It's a lengthy calculation will be.
Yeah, yeah, lengthy calculation will be there in any subject. Yeah, but that's what you have to practice, no? If you practice, the speed will increase. This is question number 1. Okay. Okay, about this topic. Okay, question number 7. Can you read the question?
Kinetic energy.
Just a minute. Energy of electron in the atom. Orbit is minus the. Okay, this is also trivial question.
So option B.
How did you find out?
B, sir.
Kinetic, oh,
B.
okay. Kinetic energy is same as this one. Energy is same as this one. C. Yeah,
B,
kinetic.
sir.
B.
Second option.
Okay. First thing is kinetic energy has to be positive. Okay. And
Yes, sir.
potential energy is
2 times of total energy.
yeah, magnitude wise 2 times and with a negative sign. So 3.4. Okay, good. So total energy, what are the different forms of energy here? Using total, no?
Kinetic energy plus potential energy will be total energy.
Yeah, it's electrostatic potential energy. It's bring two charges.
Yes, sir.
Okay, so right, the ratio of kinetic energy to total energy of electron. Oh, this is a trivial question. Can you read this question? Question number 8.
No, sir. Ratio of kinetic energy. 1:-1.
Yeah, option B. Okay, this one, ratio evidence of the last line of Balmer series and last Diamond series. This is also a good question. It's also a trivial question, right? If you know the relation.
Last line of Balmer series means
So what is Balmer series?
R into 1 by 4 minus 1 by n square, sir.
Now what is infinite?
2.
This is for Balmer, right? So let me put B. So similarly for infinite for Lyman is what?
1 by 1 minus 1 by n square.
I said
N
infinite.
final
Infinite is 1
1.
for Lyman.
Okay.
Okay. He's asking what does it mean by last line?
Infinity, yes, sir. N2 will be.
Yeah. So from infinity, it has to fall down to n equal to 2. So for similarly for Lyman, it should fall to n equal to 1 from infinity. Okay. And the energy in terms of this thing is given as what? 1 by n square, no? So energy is minus 13.6 by n square. Okay. Infinity for both the thing. E infinity is how much for both?
0, sir.
Okay. So basically you have to find E2 by E1, right?
Yes, sir.
That will give me the ratio.
4, sir.
So that is 1 by 2 square divided by 1 by 1 square. 1 by 4. Who is asking? Balmer to Lyman. So Balmer is 1:4.
No, sir.
Wavelength,
4
okay.
is to 1.
No, that's because he's asking wavelength. Wavelength
Yes,
will
sir.
give us 1 by n. Energy ratio is 1:4. Okay. So wavelength ratio is opposite. Is it clear?
Yes, sir.
So what is the frequency ratio?
What, sir?
What is the frequency
They will
ratio?
be opposite 1 by 4.
Okay. This one, electron for hydrogen atom jumps from third orbit to second orbit. Emits a photon wave when it jumps from fourth to third orbit. The corresponding wavelength will be. This is a trivial question. What is the answer? As soon as you read the question, you have to draw some small diagram or something. It's from 3 to 2. Okay. It emits a photon of wavelength lambda. So now it has to jump from 4 to 3 and let the wavelength be lambda 1. Okay. So you have to find lambda 1 in terms of lambda. Okay. So you know the relation for lambda n. What is formula for lambda n?
20 is to 7. Sorry, 20 by 7 lambda.
Yeah. So basically 1 by lambda is r into 1 by n initial square minus 1 by n final square. This is the one used.
Is a n final square minus 1 by n square.
Yeah, n final is okay. Everything is new. Okay, this is a little bit lengthy calculation. This one, a proton and an alpha particle both enter a region of uniform magnetic field B in the right angles. Radius of superpart both particles are equal in the kinetic. Try this one. Good answer.
Mhm. So same as a 1.5 electron volt mega electron volt. Mm. Sorry, what? One minute.
P1 by V2 is half. So kinetic energy K1 by K2 is square. You got the answer?
1 minute, sir. One,
Yeah, 1 is correct. So the charge of helium, this is how much? 2, right?
yes, sir.
2e. Okay, so what mistake I'm saying? This is the basic relation, no? Q will be equal to mv square by r.
Yes, sir. I took ratio of both helium and proton. For helium mass, it will be 4 m, sir. And charge will be 2 P.
Okay. For
And
m2 by m1, this ratio,
when you
helium,
divide them, you get that velocity of helium is half of the proton's velocity.
no, mass of helium is how much?
4 m.
Oh, okay, that's a mistake I made. Okay, so answer is 1. So use this relation, no?
Yes, sir.
Okay, this is starting point. And kinetic energy, I can write in terms of momentum, or we can use mass ratio also. Okay, this you don't have to do, right? It's trivial question. Question number 12. Can you read it?
Ratio of longest wavelength to the longest wavelength in the dimension. Yes, sir.
Longest wavelength means uh, shortest frequency. No, this is difficult. No? Then
No,
shortest
sir. N will be next. You know.
CBSC. So longest frequency makes sense. Okay. So this is the shortest. Okay. So minimum frequency is the next to. See, in Lyman series, the final this thing is 1, right? So the longest wavelength means it's a minimum energy difference, right? Understood or not?
No, sir. I didn't get it.
No, longest wavelength means shortest frequency, no?
That is it.
Shortest frequency means the energy difference should be minimum.
Yes, sir. Actually, energy. Okay.
So for Lyman, the minimum energy difference is between 2 and 1,
Yes, sir.
because final is always 1. So between 3 and 1, the energy is higher than 2 and 1. So the minimum energy is corresponding to 2 to 1. So that 2 to 1 transition will give that corresponding longest wavelength. So in Balmer series, the transition 3 to 2 will give the longest wavelength.
Yes, sir.
So, and you can use this relation 1 by lambda equal to Rydberg constant into z square into 1 by n square. Okay. Okay, this one, consider third. It's clear, no? This question is done.
5 by 27. Okay. Yes, sir.
Yeah, yeah, it's correct. This one, consider third orbit of helium using non-realistic approach. The speed of the electron in this orbit will be.
B is equal to that value. You have to use that value as a 3 by 137.
Yeah, you can use that.
137 into z by n, which is n value 3. diluted value will be what, sir? 0.6.
See, the ratio of the speed of the electron is asking electron, no? So it is same as a square root of the kinetic energy, right?
Yes, sir.
The value of helium. Okay. So if you know the kinetic energy, yes. So you just if you remember this from the 13.6 by n square, from that we can get
So 1.47 into 10 power 6.
option B. Yeah, option B is the correct one. So if you can use this 13.6 by n square and then into z square for helium. Okay, so from that we can get the energy, and this is the total energy. From that I can get the kinetic energy, which is negative of that, and mass
Yes, sir.
of the electron is known. So from that I can find the velocity.
Yes, sir.
This one, hydrogen atom ground state is Z by a radiation of this wave. Number of spectrons in incident spectrum emitted will be. So you understood this question?
Yes, sir.
Hydrogen atom. So lambda equal to something 975. So mu is C by lambda, right? So this will correspond to delta E. So delta E is h nu. So this delta E I have to find corresponds to in ground state. So from ground state, this thing is going to go. So this is some E final minus E initial, that is the ground state, that is equal to this one. So from this I can find N final. Is that right?
Yes, sir.
Lambda is known, so mu is known. So delta E is h nu. Okay, since nu is known, delta E is known. That is E final is E initial E1. So E1 is known. So from there I can find NF. So if NF is 3, then the number of resulting lines will be 3 to 2, and then 3 to 1, so it will be 2. So this will find NF. So what is NF?
Then final.
So what is its value?
I don't know.
Now first find delta E, what is the value? H is how much? 6.63
Into 10 power minus 34.
minus 34. And C is 3 into 10 raised to 10, 10 raised to 8. Now, okay, calculation is there. Let's see by lambda. That's what he has done, delta E. Okay, this is in electron volts, is coming out to be 12.75. So 12.75 is minus 13.6 by.
Electron also. We are using the Joule value emulator 6.63.
Yeah, here it's in Joule. From Joule is converting electron volts. Okay, because we have that formula 13.6 by n square. That is in electron volts. So 12.75 will correspond to so minus 13.6 into 1 by n final square minus 1 by 1 initial square equal to 12.75. Okay, so from this I can get n final. So this is coming out to be 2 n final. No, right? And this 4. 4 means, yeah, I don't know how to calculate. So reciprocal of this one, square root some mistake I'm making. Okay, maybe I'll tell next time. So okay, but this is the method. Okay, HC by lambda. Okay, this is corresponding delta E. So delta E is to 12.75. Okay, I have to use Z. It's hydrogen only, right? So okay. So from this I have to get n final as 4 minus 13.6 by n square. 1 by n square minus 1 by initial this thing. That is this one. So 12.75, 12.75.
So you left that minus sign, sir.
Which minus? That's fine. I can put it. Less than 1. Okay, I'll tell next time. We'll close now.
Okay.
Okay, bye.
Bye, sir.